Okay. Hello and welcome everyone to another episode of the AI co-learning program. I'm your host Bruce, and it's great to have you all with us again. In today's session, we'll explore a topic that sits at the heart of modern AI systems: how reinforcement learning is shaping the training, alignment, and deployment of large language models. So our guest today is Professor Haipan Chen, an assistant professor and the graduate program director in the data science department at William and Mary. Um, his research focuses on the use of inspired AI with technical interests in reinforcement learning, generative AI, and optimization, and application domains including health, environment, and the physical science. So in today's talk, Professor Chen will discuss reinforcement learning for language models. Welcome, Professor. Now the floor is all yours.
Yep. Thanks. Thanks for having me, and thanks for the kind introduction, Bruce. Like Bruce introduced, today I'm going to talk about how reinforcement learning can be used to support the large language models tasks. I'll first talk about more popular methods like IOHF and reinforcement learning from uh, verifiable reward, which are like more on a fine tuning stage. And then I'll talk about like what I call finer tuning, meaning that we're going to use reinforcement learning to do more downstream fine tuning of downstream tasks like agents, and so on. And at last, I'll talk about some of the ongoing works in our lab, which is like another level of lightweight reinforcement learning models, which I call auxiliary policy models, which are really lightweight, like sometimes just an MLP, but these have been proven to be very useful as well. So I'll start showing this kind of visualization of the evolution of different large language models over time, where the x-axis is the time, the y-axis is the MMLU, which is the kind of metric to evaluate the capacity of the different language models. So from this visual, we can have a lot of observations, among which, first of all, this I guess a lot of you uh, should have pretty much noticed it. The first observation is that the scaling law, right? If you look at like vertically, if you fix the time stamp and you look up uh, towards the y-axis, you can see like the larger models usually tend to be more powerful, right? You can see the clusters of bigger models here, where the size of the dots means the size of the models. So scaling law holds at large, but at the same time, another observation is there are outliers. So there are two notable outliers are, first of all, ChatGPT or GPT 3.4 Turbo, and then the other outlier is the DeepSeek R1. So for these two models, although their sizes are not as large as some of their competitors, you can see they're fairly small, but their capacity is pretty large compared to uh, models with the same sizes, right? So the question is, what are the techniques that are like kind of driving them to be capable, but they're still at the relatively smaller size? So let's look at the ChatGPT or its sibling, which we call InstructGPT, which is the product of OpenAI in 2022. So this is a figure showing the different the performance of these of the Instruct GPT models, which are the two lines on the top, which are like trained by a reinforcement learning algorithm called PPO. There are different versions of that, and compare with the baselines, which are just fine-tuned with these SFT, which is called supervised fine-tuning, and the Orange-Node GPT models. So you can see that a key observation is that, first of all, of course, the scaling law is still there. Whenever you increase the size of the model, then the performance is going to be better. But also, if you compare this dot, which means that we have a 1.3 billion model that is trained or fine-tuned with PPO versus like 175 billion model, which is fine-tuned with SFT. So you can see that even a much smaller, like 100 times more smaller model is performs better than 175 billion models, right? So that's one. So that's a kind of a critical moment of all of these LLMs. Another outlier is DeepSeek R1. I'm pretty sure that most of you are familiar with DeepSeek R1, and one of the most one of the advantages of DeepSeek R1 is that the training cost is really small compared to some of the larger models, right? For example, here, this is the training cost, which is approximately 5 million for DeepSeek R1, and also DeepSeek V3. Whereas like training some of the Llama models, cloud models, they're like more than sometimes 6 times or sometimes 10 times the training costs of DeepSeek R1. But at the same time, you can see that the performance evaluated by all kinds of different benchmarks shows that DeepSeek is actually performing as good or even better than like somehow by that time the state-of-art OpenAI O1 models, which is trained actually using much higher cost than the DeepSeek R1 models. Right. So that's kind of gives us an impression like, we might wonder that what are the techniques that are behind these two models, right? So actually, there are two key techniques related to reinforcement learning behind these two models. For instructed GPT, so RLHF, or reinforcement learning from human feedback, is one of the key techniques. Whereas for DeepSeek R1, reinforcement learning with variable reward is one of the key IO techniques. And of course, we also have the GRPO as another key IO technique, but I'm just going to focus on these IOVR. Well, so if so given these inspirations, you might wonder like what should be the next, right? So there are lots of discussions, especially like after the beginning of this year, where DeepSeek R1 came out, and in this podcast by Darkesh Patel, so Ilya Sutskever had an interview with him, and it was very inspiring. And one of the key takeaway from that interview was that he thought like, so we're already at a critical time where the data size are kind of plateaus. The effect of the larger data sets, the effect of the larger model is kind of platooning, whereas it's really like the AI innovations in terms of methodology that are driving the capability of the current large language models. And I quote him like, the key question is if you're scaling 100 times more data or model, would everything be so different? So that's a kind of a question that we want to explore in the future. So but that kind of motivates us, like reinforcement learning could be potentially a solution or answer to that. And in another scenario where Andre Karpathy was commenting on I think a few key innovations in 2025 LLM year in review, and he listed reinforcement learning from verifiable rewards as the number one kind of innovations in the LLM domains. So both of these like top AI influencers' opinions are kind of indicating that in the next stage of LLM research, where we should look for innovative ways of improving the models instead of just like increasing the scale of the models, and potentially reinforcement learning can be a very useful tool to make it happen. And I would like to share another very popular view that was like a blog by David Silva, who was the lead behind a lot of important reinforcement learning projects from DeepMind, including DQN and AlphaGo, and Rich Sutton, who was one of the 2022 Turing Award for his contributions on reinforcement learning. So they wrote this blog about welcome to the era of experience. And the key takeaway here is that as along the times that there are like ups and downs of reinforcement learning, where why here is kind of the attention to reinforcement learning. You can see that when Atari games like DQN came out, it really demonstrated like reinforcement learning can achieve superhuman performances in playing video games. And then it kind of increases towards one of the peak where AlphaGo came out, and even AlphaZero came out, which needs zero human input data. So, and this is called the era of simulation, because a lot of these success of IO happened because of seamless simulations, like millions of episodes of training. But later on, people kind of felt its IO was very limited, right? Because they only work on simulations and video games. What about the future, right? And then because of that, like people started to think that IO is after all just a toy, and it's very limited until like the era of like the era of human data came out, where in training ChatGPT, people are starting to use IOHF, and then even more like here, where people are starting to use DeepSeek-R1 or reinforcement learning to train to really pure reinforcement learning to train LLMs to improve their performances. So, and this era is called by these two AI researchers by the era of experiences, meaning that in the future stage, we no longer will depend so much on human data, but instead reinforcement learning should be able to explore experiences by repeatedly, seamlessly playing or interacting with the environment. In this case, just under the context of LLMs, so IO algorithms should be using LLMs to repeatedly interact with the environment, which could be like computer use or tool use or web search. all kinds of or math, reasoning, all kinds of different tasks. And IL should be able to collect examples on its own and then gradually improve. So that's kind of the projected trend, but does it hold? And that's an unanswered question. That maybe that's one of the future directions that we should explore. Well, so given all of these popular opinions, I think what I think of as of today, the reinforcement learning for LLM research is still like the two mainstreams are RLHF. It's becoming more and more mature. It kind of becomes a standard paradigm for fine-tuning any large language models. And then ILVR is works for domains where you can naturally and automatically obtain the verifiable rewards. And there are some innovations in terms of IO algorithms. For example, this GRPO and its variants are still improving the stability and efficiency of the LLM fine-tuning, but still critical challenge of like even making IO even more useful is how would us do like better reward design, and how do we design reward functions that are generalizable to all kinds of different domains, in addition to these math, coding, and reasoning domains. And lastly, there are starting to have more and more increasing usage for using IO to do what I call finer tuning, which means that we're still like fine-tuning the LLMs, but these fine-tuning are at a much smaller scale, and they're mostly for specific tasks like tool usage, planning, or web agents, for example. And what I think in the future, one missing piece or promising direction is still there are going to be a lot of more increased usage of reinforcement learning for finer tuning in all kinds of different LLM downstream tasks. And there are yet a lot to explore because there are still a very limited usage of IO. And another important and promising direction that I think is what I call auxiliary policy models, or APMs. So in APMs, basically, we're going a step further. Instead of fine-tuning the LLM itself, we're only using a very, very small, lightweight, separately trained policy models that are going to be used to steal the optimization of the downstream LLM task. I'll talk more about this in the later slides. Well, so overall in today's talk, this is kind of the flow of today's talk. I'm going to first introduce some of the mainstream practices in reinforcement learning for LLM fine-tuning, including ILHF and ILVR. And I'll use some examples to kind of illustrate what is finer tuning in a lot of the downstream tasks. And later on, I'll introduce some of the projects that are done in my own group in these APM scenarios. Okay. So first of all, what is reinforcement learning? Reinforcement learning is a type of machine learning method where an agent learns to make decisions by interacting with an environment. Right? There should be an environment, and there's an agent that the agent interact with the environment and receive feedback from the environment in the form of rewards or penalties. And then the agent is going to use that reward or penalty to update its knowledge or policy to make better decisions in the next time. And these two AI scientists are the 2024 Turing Award winners for their contributions to reinforcement learning. So reinforcement learning, in some sense, was kind of the way that a lot of humans learn how to make decisions in the real world. For example, if you're an infant, you try to explore all kinds of food. Sometimes it's sweet, you like it. Sometimes it's so sour and you don't like it. And next time maybe you see something similar and you won't take it, right? And if you're a human like this and you see you ran into a bear and this time, and you're somehow you learn that it's not running into a bear is not a good thing. So next time when you see a bear, you probably won't run into that bear again. Right, so humans appear to learn behaviors from this trial and error. So we try a lot of different things, we explore things, and we learn things from all these experiences. So what exactly is reinforcement learning? So in this example, we have an environment, which is the bear, right? And we have an agent, which is the person. The agent makes observations from the environment, which is called state, and then takes an action according to the state. In this case, they either run away from the bear or run into the bear. And then these actions going to interact with the environment, and the environment is going to emit some reward signals to the agent. In this case, if you eat something sour, you get a -1 reward, for example, and if you eat something sweet, you get a positive reward. And this reward is going to help the agent to update its policy. And that policy is going to guide the agent to make better decisions in the next time. So overall, the agent observes the state, ST takes an action, receives the reward, whereas the environment receives the action, emits the next state, and emits the reward signal as well. And then this iterates over time until it reaches the so-called terminal state, where in this case, if you were like hit by the bear, that's the terminal state, or you just escaped and you stay alive. Or more formally, we often use this concept called Markov decision process, or MDP, as the top to define this IO problem, where as a finite set of states is a finite set of actions. We have a state transition probability matrix and a reward function and a discount factor, which kind of reflects how you should treat future reward. It's usually a number that's between 0 and 1. And given this MDP problem, then there's this idea called policy, which is a probability distribution over actions given the states. And the goal the goal of the agent or the policy is to maximize the expected return or sum of rewards over time by finding the best policy. Right. So that's overall the IO problem. And reinforcement learning has been very useful even before it's used for LLMs. One of the most successful use cases using IO to play Atari games like this one. That's where like people really start to realize that that reinforcement learning can be useful. And it has been for not sure if you guys are aware, reinforcement learning has been there for I think almost 70 years, and it came out around the like 1950s, and a lot of the naive IO ideas were out, and one of the founders, Andrew Battle, which I quote from him from the Reinforcement Learning Conference 2024, he said at the beginning, machine learning is reinforcement learning. So people are starting to use develop all kinds of IR systems, but they barely worked at that time. But when DQN came out, this is where really like people start to believe that reinforcement learning can be useful. This is because of various reasons, including like the hardware, the improvement of the hardware, and also like DQN uses convolutional neural nets to represent the states, along some other technical improvements. And then later on, people have started to use reinforcement learning to all kinds of applications. For example, data center control to cool the data centers, and even nuclear fusion control. But this is like in a simulation environment. And robotics control has been a very important useful application of IR as well. And eventually, what made IR to be like achieve the first peak of attention from the public is when it developed AlphaGo, which is an AI agent that is able to play one of the hardest board games in the human history, and it beat the by the time Li Shidou, who was the world champion in I think 4 out of the 5 games. And later on, there's even more improvement of AlphaGo. And nowadays, whenever you play Go, and actually reinforcement learning or AlphaGo has been kind of the AI has been the digital coach of all the professional players. So again, I'm looking at this curve of the attention of reinforcement learning over time. You can see that so if you're a reinforcement learning researcher, you kind of have the feeling of like riding a roller coaster where you have ups and downs. Sometimes you feel like it is really working, right? When Atari came, when DQN came out, when AlphaGo came out, and this is like around the time where I started studying reinforcement learning, and I feel like it really works. But later on, I feel it doesn't, because it only works at very similar, very limited scenarios. By that time, I was trying to use reinforcement learning to do like pricing optimization of the road tolling systems, and it works to some extent if you have a very good simulator and you have seamless training examples, and it works. But it only works in simulators, right? Whenever you want to deploy that in a real system, there's always a lot of issues, including real to sim to real gaps. And then, so because of that, a lot of people starting to lose faith about reinforcement learning, especially when the LLMs came out, and this drew much more attention than reinforcement learning in the AI community, and people start to lose faith and lose attention to reinforcement learning until like 2022. ChatGPT came out, and one of the key techniques behind ChatGPT is actually reinforcement learning, or IRHF in more detail, more specifically. So, yeah. So that being said, reinforcement learning has been very useful, so the next step, we're gonna talk a little bit on more specifically what is IRHF. So I think it's a typo. This should be an environment in this case. Okay. But anyways, so in IRHF, so the original environment was a bear, but in reinforcement learning from human feedback, it's still kind of this same pipeline of the IR problem, but it's just that in this case, the environment is the humans, right? The humans act as the environment and gives the feedback to what was generated by the LLMs. So in this case, the LLM is the agent, and it uses the policy to do the next token prediction, right? The policy is basically representing the distribution of the next tokens. It's a kind of a distribution of all the vocabularies, and it's a big vector. And whenever the LLM is gonna take an action, meaning predict the next token or a series of tokens, and then at last the human environment is gonna give a feedback whether this is a good token or token sequence. So that's the basic idea of like still follows this same schematic framework, but it's just that in the era of LLMs, the environment becomes a human. The era of ILHF, the environment becomes a humans, and the human's gonna generate the human feedback. The state here is the user prompt plus the tokens that are generated by the agent so far. Any action is actually just the generation of a token. So here we usually assume that in reinforcement learning we have this Markovian assumption that the current state is going to reflect all the historical events. But here, if we want to, we can still, this still holds in the sense that the state is defined as the entire prompt plus the token history. And this is a kind of a visual of the three steps in fine-tuning LLMs using this ILHF paradigm. And it sort of became the standard paradigm in fine-tuning any LLMs after it came out in 2022. So basically, it did it in 3 steps. In the first step, we always still use the human demonstration data to do so-called supervised fine-tuning. In this way, it's just like any supervised learning techniques. You're going to have a base LLM, and the base LLM is going to generate tokens, and you will have a human that is going to tell you if this is a good or a bad token. And you're going to use the supervised learning loss to fine-tune this model. So that's still like SFT. And then step 2, we're going to use the human demonstration data. For example, we're going to given a prompt. We're going to use the LLM to generate 2 answers, and then humans are going to rank these 2 answers. And this kind of preference data is going to be used to train a so-called reward model. So basically, the reward model is going to encourage tokens to if the sequence is good, then the reward is higher. Otherwise, it's going to be lower. And you're using tremendous amount of data to train this reward model. So in the hope that it generalizes well to a lot of out of domain tokens or examples. So that's step 2. Once we have a reward model, then in this case, we can use reinforcement learning to train this agent, right? Or to train this LLM. So if you look at step 3 here, this reward model really is the environment, right? And the policy here is the LLM agent. What it does is that it's going to take the prompt as the input, which is kind of the initial state, and it's going to repeatedly generate different answers, and it's going to generate the answers or a sequence of tokens, right? And the reward model is going to give the reward, and this reward is going to be used by the LLM agent to fine-tune its policy, which is the LLM itself. And this whole pipeline is actually done by this RL algorithm called Proximal Policy Optimization, or PPO in short. So what is PPO? If you're familiar with reinforcement learning, you can see that this is a very typical training pipeline of reinforcement learning. It does it in different iterations In each iteration, it collects a bunch of data samples. For each of these actor here, we're gonna first run a policy, which is represented as pi theta old. Theta old means that the old policy. It's gonna run the policy in the environment for t time steps. In this case, it's gonna just unroll or do next token prediction of a couple of times in the LLMs. And then afterwards, gonna compute the advantage estimates, right? So advantage estimates means that it's just an estimation of how good the current tokens are. And it's defined in this case here, where these are just parameters that are going to assign weights to the different time steps. And our t plus L is the current steps reward. And this is like a so-called value function. And this is a value function of the next step. And this is a value function of the current step. So basically, this advantage function evaluates how good your current action or token is compared to a certain baseline as evaluated by the value functions. So, and it's gonna compute these advantage estimates, and then afterwards, it will use these data sets or data points to optimize the policy. And it's going to be optimized using a loss L, which is defined here. So basically, what this objective says is there's a long story to this, but overall, what it says is if your advantage is good, advantage is large, meaning your actions is good, then you're gonna tweak your parameters to go toward that actions. Right. Otherwise, you're gonna tweak your parameter theta, which is a policy parameter, to go in an opposite direction of generating this action. Right. So that's the key takeaway. And this was PPO was originally derived from policy gradient theorem, and then later on with a lot of evolutions, including, for example, TRPO, which was trust-free region policy optimization. But a key trick here is this clipping operation, which basically kind of limits how much you can update in a single iteration, so that it becomes more stable than its previous version, which is TRPO. And it also uses so-called likelihood ratio, which is basically you're gonna, or important sampling ratio, which basically to kind of cancel out the mismatch between the so-called behavior policy pi theta old, which is the policy that you use to collect examples, and the target policy which is the policy you're trying to optimize. So because there's a mismatch, this kind of like ratio is going to cancel out the mismatch between the two, so that in expectation is going to be an unbiased estimation of the advantage. Well, so, and this is the again going back to the result of InstructGPT. A key takeaway is that like using reinforcement learning pipeline to fine-tune all these fine-tune these LLMs, then even in a much smaller, like 100 times smaller model, it's gonna achieve better performance than if you just use SFT to fine-tune 175 billion model, which is pretty impressive at that time. And then, so the third kind of, so these are the two moments where people are starting to believe that IO can be useful. And the third moment is here, I believe, where IO reinforcement learning from verifiable reward came out. So what is IOVR? So if we're taking this, the previous slide, we can see actually IO from reinforcement learning from from experience is the next step to go, and it's that and this is exactly what or in more specifically, a variant of reinforcement learning from experience is reinforcement learning from verifiable reward. Or in other words, what I think is ILVR is a special case of reinforcement learning from experience. Well, so in this example, we're still, whatever the IL pipe or framework or pipeline it is, so it still follows this kind of MDP or IL problem formulation. It's just now in the environment, instead of a human, that's going to determine how good these examples or tokens are. In ILVR, we have a automatic verifier system. And still the state is the user prompt plus the tokens generated so far. And the action is still the generation of token. But in this case, specifically in training DeepSeek agent, DeepSeek model, they actually formulate the generation of tokens as a reasoning chain of thought. And then the reward function is just given by this verifier system. Okay. And the agent here again is still the policy, or still the LLM, and the policy is still just the next token distribution, or the LLM itself, right? And that's the overall training pipeline of DeepSeek R1. So it's pretty kind of complicated because it has a lot of different stages, and it iteratively uses SFT and reinforcement learning to train this. So we're going to first look at the first stage. Okay, so given a base model, which is called DeepSeek V3, it uses the reinforcement learning algorithm. It kind of formulates the token generation process as a reasoning chain of thought reasoning procedure, and then you use the accuracy and format of the generated tokens to update the policy. And then through this one iteration, what it generates is called DeepSeek R10. And this IL algorithm behind it is a slight variant. It's a variant of PPO, which is called GRPO. So you can see that in large, it's still largely very similar to PPO in the sense that it still do iterations over time, and at each for each prompt, it's going to generate sample a group of outputs using the same PyOD, and it's going to compute the reward and so-called group normalized advantages. And these advantage values are the key difference of GRPO compared to PPO, which I'm going to talk more in the next slide. And again, after we collect these experiences, intuitively, if we have an LLM, we use the LLM to generate a lot of tokens, and we get the rewards, and we understand how well these tokens are, and then we can use this to optimize the new policy, right? So that's the high level idea, and this is kind of the comparison of PPO versus GRPO. You can see that they're very similar in the generic pipeline. Both of them still follow the IO pipeline. It's just in PPO, it generates like whenever it generates one output, it's going to use a value model or a value function to estimate the advantage, and then use that advantage to update the policy model. Whereas in GRPO, it will generate a group of outputs and then use the relative reward value or relative advantage value from this particular group of outputs, and then use these advantage values to update the policy model, right? So because it generates a couple of outputs at the same time in a group, and they use the relative comparison of rewards, so that's why it's called group relative policy optimization. So in more detail, So these two loss functions look like this. You can see that as still like in terms of format, both of them has this likelihood ratio. Both of them have this clipping trick. But the real difference lies in how do they calculate the advantage values, right? So in PPO, it was calculated by this so-called TDRO, temporal difference arrow, which is basically the reward plus next state's value function minus the current state value. Whereas in GRPO, it doesn't rely on the value function. And you can see because of that, it's more it saves a lot of memory for like maintaining the value functions. Therefore, it's usually like it has lower cost, and it tends to work more efficiently, especially for large language model training. So, and here, as I said, a key takeaway is that GRPO doesn't rely on a value function. And that's how the DeepSeek R10 works. So by DeepSeek R10, it's really like just one iteration of the GRPO fine-tuning. We can see that after couple of thousand steps, it's already like the accuracy is like surpassing human participants in answering these AMY dataset questions. AMY basically a set of mathematical questions for high school and undergrad level. So that's the first step, and you can see that afterwards you will run into a few different iterations of SFT, IO, and then SFT and IO again. So for each of these steps, there are going to be intermediate models, and if we put them together, they have a final evaluation of the performances of all of these different models. So you can see that after a lot of iterations of these SFT plus IO, it generally does improve the overall performance over different benchmark. All right, so these are as a takeaway, DeepSeek R1 automatically generate. It uses a verifiable reward system, which is like, for example, math questions or coding questions, where we can automatically get the reward for these generated tokens instead of human preferences. And in this way, we can actually generate large amounts of data in a much larger scale than human preference data, because like human preferences data is limited eventually. And another innovation is that if we kind of decompose the generation of tokens using a reasoning chain, this is naturally like formulated as a real reinforcement learning problem, right? And then lastly, the usage of group relative policy optimization versus PPO is actually plus iterative IO training. It's actually improving LLMs at scale. So this is pretty much about fine-tuning using reinforcement learning. So next, I'm going to talk about so-called finer tuning. By finer tuning, what I mean is really like tuning it's still fine-tuning LLMs, but like fine-tuning LLMs in achieving a lot of the downstream tasks. So these downstream tasks include, for example, using LLMs together with tools, and then use LLMs to do as a web agent, or augment LLMs with retrieval augmented generation, and also, for example, to increase the memory or manage the memory of LLMs. Right. So in a lot of these scenarios, there's actually a lot of decision makings to make. For example, in tool use, we have to decide which external API or tool to use. Right? In web agent, we need to decide which is the next move. Is the LLM or the agent gonna scroll down the screen, or is it gonna click this particular link. And in RAG, we need to rank a lot of these examples in memory. We have to manage the memory to more efficiently to deal with the context, especially when the context is really long. So what I think in the current practice of like steering or decision making in this LLM downstream task can be made into two categories. The first category is just to treat the optimization as a training-free heuristic. For example, in tree search is kind of a heuristic that's used in some of the reasoning frameworks. And another one is what I call finer tuning. So basically, we're still using the IO pipeline, but it's just that now this pipeline is based on a specific downstream task instead of a lot of all kinds of different tasks. I'm going to briefly talk about these optimization as a training-free heuristic. There are a lot of such examples. Some of these are famous examples, including, for example, in RAG. What it does is basically using ideas like cosine similarity to rank the examples. And in tree of thoughts, it uses a tree search algorithm, and it estimates the utility of different paths based on some estimated scores. And in speculative sampling, for example, if you're familiar with SPS, it's a way to accelerate the LLM inference. And in there, people are also actually using tree search algorithms to search for better speculative sampling strategies. I'm going to talk about this a little bit more in the third part of the lecture. Whereas in the second part, which I call finer tuning, this is really where reinforcement learning can be very useful. So there are all kinds of different examples. For example, in tool use or web agent, in RAG or memory. I'm just gonna briefly go over all of these in the next few slides. And again, what I still believe, no matter like what kind of IO algorithms they use PPO, GRPO, or what kind of data sets they use, eventually they still follow this kind of ILVR, reinforcement learning from verifiable reward framework. It's just now they have all kinds of different definitions for the environment, states, actions, reward, or agent itself. So the first example is the tool use. So here, basically, the environment is, in addition to the just the simple verifier system, it also uses all kinds of external tools, and the execution of these tools are going to output the feedback on whether the calling of a tool is a good call or a bad call. And the state is just still like the user prompt, but it's just it's going to include the tool calling history and also how well these calls have been executed so far. And the action is, again, just the generation of the tool calling instructions, right? In this case, for example, a lot of papers just treat the different tools as like special tokens, and they're just going to generate those tokens as the actions. And the reward, again, is the verifier feedback. In this case, for example, if you're going to use a math or a calculator, then you can know that if your calculation is correct or not, right? And that's the reward you're going to use to train or fine tune your LLMs. And the agent is here again is still the LLM. In this case, in this paper, it uses a Q1 model as the LLM and uses this automatic feedback to fine tune this Q1 model. And the second example is a web agent. If you're familiar with web agents, and you can immediately kind of makes sense here, right? Because the environment is like, in addition to a verifier system, you have a website engine that's gonna that where the agent's gonna interact with. Is the agent is gonna play, and in this web engine, it's gonna the state is the, for example, the query. If you want to buy a flight ticket, and the action history so far, plus the website HTML, which is kind of the current status of your agent. And the action is to generate the next move, for example, to click a link or scroll down or search some keywords, a lot of different actions. And the reward, again, is verifiable feedback, and whether you're succeeding in searching something, or whether you're successful in booking your flights. And again, the agent is a web agent. And in this particular paper, it uses a Llama model to act as a base LM or the policy. And a third example is the RAG system. In this case, if you have a RAG system, then you have the search, because in the RAG system, what it does is it has a rewriter to generate your query or rewrite your query, and then you have a search engine as a retriever, and then you have a LM as a reader. And when you combine this, and then if you're inputted have an input query, you go through all of these three processes, and then you can generate an output, and that output is going to be used to get the reward signal, right? So in this case, the state is just the query plus the tokens generated by the rewriter so far, and the action is generation of a token by the rewriter, and the reward is still the verifiable feedback. And here, in this particular paper, it uses a small language model, which is T5 large. It's actually a BERT model, not a GPT model, as a rewriter. But again, it's if you wanted to fine tune it, still there's still substantial computation cost. And the last example is memory management. I think of a long context example. If a very long context, you have a memory to maintain. So in those cases, you have to update your memory to more efficiently generate what you aim for. So in this case, the environment is a memory bank plus the frozen LM as an answer agent. That's not going to be tweaked, but you still have a verifier system that tells you how good your generation is. And the state is the retrieved memories plus the new information, the actions, what kind of operations you're going to take. And the reward is, again, the feedback from the verifier. And your agent is just LM as a memory manager, which in this paper is using ChatGPT model to do this. Well, so you can, like, from all of these examples, you can see that finer tuning is great, right? It works. I haven't showed the results, but you're very welcome to check these papers. They have most of these papers, if not all, have shown substantial improvement compared to models base models which haven't been IO finer tuned based on the specific tasks, right? But still, my question is it really necessary to use these large models to still pretty sizable models? So there are a lot of concerns. For example, if you're going to finer tuning LLMs, it usually leads to model bias, because if you train that model based on your specific tasks, you're going to somehow inject inductive bias based on the specific tasks, right? So because of that, will the LLM still perform generalize well in tasks outside of these fine-tuned domains? So that's a big question, right? Another question is still, it needs a lot of substantial compute. Even with like 7 billion, 1 billion models, you still need a pretty decent GPU to fine-tune these models. And it takes a lot of energy, right? And lastly, since you need to tweak these models, you definitely need white box access to these models in most cases. So the question is this really necessary? So that leads to the third part of this lecture, which I'm going to talk about auxiliary policy models. What are APMs? So it's not, if you play StarCraft or Warcraft, I know what you're thinking. It's not the action per minute, but this is really the ideal APM is to use lightweight reinforcement learning, very lightweight, sometimes even like MLP models, to train separate small models to steal these LLMs in the downstream tasks. Okay, so but it still follows the ILVR framework. So later on, you'll see that then they're still holding a lot of these formalizations. I'll use two examples so you can see that both of these examples still follow the MDP formulation, and there's all kinds of different components in this MDP. But the difference is that the LLM itself is going to be frozen. We're not going to change that, but it's going to be treated as part of the environment. So why do we care about it? So there are a lot of advantages of APMs. First of all, it's very flexible, right? Since we don't need to touch the LLMs, there's no modal bias or inductive bias injected to these APMs because there's not going to be modal bias that are injected to the LLMs themselves, because the modal bias is mostly injected just to the APMs, and they're dedicated to the specific tasks. And it has much lower training costs. In the examples I'll show, you can use very low-end GPUs to train these APMs with very short time period. And also, the inference cost is much lower, right? Think about just an MLP. So these are critical for a lot of scenarios. For example, if you have time-sensitive tasks, if your goal is to accelerate the LLM inference at the first place, you have to use this low-cost policies. And in sometimes, if you're have edge computing scenarios, you don't have a lot of capacity in GPUs to host the large models. And eventually it works a lot of times in black box models. So in the next half an hour, I'll just use two examples from our group to kind of exemplify how these APMs can work. Okay, these are joint works with Cheng'an Wang and Daniel Shu, who are PhD student and undergrad student in our group, and Mohammed Wasif Nafi, who was then an undergrad intern in our group, and Maiqi Zhang and Yanfu Zhang are Maiqi Zhang is a PhD student of Yanfu Zhang, and Yanfu Zhang is my colleague at William Mary. So I first talk about this example where reinforcement learning can accelerate or improve speculative sampling. So a little bit background on SPS. So this is a key technique used to accelerate the inference efficiency of LLMs. It works by parallelizing token generations through a draft and then verify cycle. So what it does is it maintains two models, a draft model and a target model. Instead of directly using the large target model to directly generate tokens, it first uses a smaller, you can see the smaller model here, to generate a lot of draft tokens, and then uses the large model to verify if the drafted tokens are correct. If they're correct, they're going to be accepted. And that, because the inference cost of the smaller models is much smaller than the large model, so this naturally improves the inference efficiencies of LLM inferences. So So that's the original idea of SPS. It was originally proposed by a bunch of scientists from DeepMind and also Google Research. And since the advent of these models, there have been a lot of improvements. Notably, like recently, there have been efforts that instead of using a chain, proposing a chain, draft a chain of tokens, what they do is to draft a tree of tokens. So they can use because if they propose multiple token paths in parallel, then you can use this kind of tree structure and use the target model to find the token path that works that follows the best with the distribution of the target model, and in this way it largely accelerates it further accelerates the speed of the speculative sampling frameworks. And so nowadays Eagle 2 and Eagle 3 are two of the current state-of-art models for speculative sampling, and they're actually being integrated as like standard pipelines in some of the famous frameworks like VLMs and SGLang. But one gap in these tree-based models is that they rely on static hyperparameters for the tree structures. For example, they will have a fixed total number of tokens that are allowable, and they have a fixed allowable tree depth, or so-called expansion factor, which basically means they allow, for example, the top 2 tokens to expand in a single layer of the tree. Right, so this actually greatly limits the flexibility of this SPS framework. So, motivated by this observation, we propose this called re-SPS. Basically, we're going to use IL to first to dynamically decide the draft tree hyperparameters. We're going to use IL to decide how many total tokens are going to be drafted. And also what's the maximally allowable tree depths, and how many tokens are going to be expanded at the same level at the same time. So because of that, the intuition is that given different kinds of complexity of the prompt, there should be the drafted tree should have different structures, right? And following this idea, we can see that we can naturally again formulate this into a Markov decision process, where again the environment is the frozen LLM. We're treating the original LLMs as a part of the environment, and we're using also part of the environment is the speculative decoding framework, or the task itself. And the status, the prompt plus all the previous tokens, the action is just like deciding the tree structure hyperparameters. And the reward in this case is it's kind of naturally designed, because the goal is to accelerate the inference. So it's naturally designed as the throughput of the LLMs, or in other words, the token bytes per second. And notably, a big difference in this framework compared to finer tuning is that we're using the so-called APMs. Instead of using a large language model itself to decide all of these actions, we're just using a very small 2-layer MLP to just kind of make these policy decisions. And the motivation is very straightforward, because if you're going to use a large model to generate this optimization, and then you're going to have a lot of overhead, right? Because each policy call is going to generate a lot of computation overhead. Therefore, an APM is an ideal solution for these kind of time-sensitive scenarios. Well, so there are some additional tricks that we developed to overcome these computational overhead issues, because even with a very small MLP, we still, one straightforward way of generating or representing a state is to use some decently small number models like sentence BERT, for example, several hundreds of millions of parameters. But even so, it still incurs substantial computational overhead. So one of the tricks that we use is, instead of using this sentence embedding, we directly use the hidden vectors from the target model, which is part of the speculative decoding or EAGLE framework. So I'm going to skip the details of the rest, but the key takeaway is still, like, in this schematic framework, we are formulating this entire procedure as an MDP, where the state is here represented as a hidden state of the target models, and this small APM IO policy is gonna take the state and generate the actions. The action is gonna guide the generation of the draft tree tokens, and then again, these drafted tokens are gonna be passed into a target model to be verified, and then eventually generate the automatic reward that is further gonna be utilized to train the APM in this case. Well, so in terms of experiments, we tried our evaluations on three different kinds of target models, including Llama 3.1 8 billion, Vicuna 13 billion, and Llama 3.3 70 billion models. And we tested on 5 benchmark data sets. And what is, I wanted to note that these like training an APM can requires very limited GPU resources actually. So you can see that the 8 billion, 13 billion models works or runs on a single NVIDIA A40 GPU with 40 gigabytes of memory, whereas the 70 billion model was run on 4 NVIDIA H100 GPUs. We used 4 NVIDIA H100 GPUs just to accelerate the inference. But if you just want to train a small APM, which is actually represented as a 2-layer 128 by 128 multi-layer perceptron. So it's very small. If we only wanted to train this, even 1 or 2 H100 GPUs can actually work in this case. It just takes more time to run. And all of these experiments are using PPO as the standard IO algorithm. And you can see that noticeably the training time is very affordable. In training the two smaller models, all of these models are like trained around 10 hours. Right, and this is the major results. So you can see that across all the different backbones, across the different benchmarks, these are different methods. We can see that our method, on average, is always the best. And compared to the state-of-art EAGLE-3, we can see that 8 billion model has 1.03 acceleration on average, 13 billion 1.04, and 70 billion 1.06. So this is quite meaningful in the sense that if you think about the current energy consumption of a lot of these LLM inferences, right? If you can reduce the energy consumption just by this, maybe 3% or 4%, is just huge. And these are achieved with very low effort, right? Because we only need to train these APMs with like 10 hours of GPU time, and afterwards we can keep using them repeatedly. And another noticeable observation is that you can see that with larger models, the acceleration is actually higher, meaning there kind of indicates that with larger models, the capacity of further acceleration is going to be larger. So it's kind of projected if we have several 100 billion models, then it's going to be even larger acceleration. Well, in the second example, I'm going to talk about how reinforcement learning can be used or APM can be used as a tool to do in-context knowledge editing. Background on knowledge editing. So basically, the motivation is that if you have a trained model using the knowledge up to a certain point, for example, if you are asking an old model who is the current prime minister of the UK, a model which is trained, like for example, between before 2023 or 2024, it will probably say Rishi Sunak has been the prime minister from 2022, right? But if a newly updated LLM, it should not answer Rishi Sunak, but instead you should answer Keir Starmer is a current PM of UK, right? So what knowledge editing is trying to do is to use to inject this knowledge into this model, and in context knowledge editing does it in a in-context learning way. So it doesn't change the model itself, but it just does it so by in-context learning. So hopefully, if we inject some knowledge, like Keir Starmer is a UK PM now, and hopefully the model is going to answer that Keir Starmer is the current prime minister of UK. So that's in-context knowledge editing. In some of the popular frameworks, for example, in this IKE paper, what it does is it will use a retriever to retrieve the number of in-context examples to be fed into the prompt, and they will use a static retriever, and they'll also fix the number of examples that's going to be fed into the prompt. But you can see the issue here, right? Because the questions are different. Some questions are harder than the others, or more complex than the others. Like some are like more popular knowledge, some are more less known knowledge. So intuitively, the retriever should be dynamically adjusted, and the numbers of examples should be dynamically adjusted based on the queries or the questions, right? And that's our idea. So we're proposing this dynamic retriever for in-context knowledge editing. So basically, we're going to adaptively adjust the ranking and number of examples per query. And this was done actually by this idea of auxiliary retrieval policy model. So basically, it incorporates the response correctness as reward signals, and it uses signal to train an APM. Okay. So again, you can see that this can kind of follows the general MDP framework. So in general, if you hear a key idea here is to treat this dynamic retriever as APM, whereas treating this a lot of the other components as part of the environment. So in general, I'm going to skip a lot of the details, but the high-level idea is to the environment is the frozen target LM plus the in-context knowledge editing task and feedback. The state is the query plus the candidate return examples in a pool, and the action is ranking and selection of examples for the prompt. And reward is again very straightforward. If the output matches the correct answer, it's +1; otherwise, it's -1. And a key innovation here is that we're using a very lightweight, just a linear head after frozen sentence birding model. So we're not going to train the sentence bar. The sentence bar is just gonna use to extract the embedding of the queries. And afterwards, we're just using the linear head as the APM here, as the policy. All right, so in terms of experiments, we evaluated that on 3 data sets, and we used different kinds of metrics, where ESR is basically the accuracy of the edited facts, and PC kind of a consistency across rewarded queries, kind of a way to evaluate the generalizability of these of the models. And then a retain rate is kind of preservation of unrelated original facts. So all of these metrics are like better, higher values are better. And in terms of the APM training, it's really lightweight. So we have the same frozen LLM backbone, which is a target which is gonna be edited. We have the BERT small model, which is 29 million, as the frozen encoder. We're not training or fine-tuning that, but instead we have a trainable linear layer as the APM. It's very lightweight, and we only use 300 examples for the training. And all the training has been done using a single NVIDIA L4 GPU with only 24 gigabytes of memory, and the training time is less than an hour. Despite this very low effort of training, we can see that across like all the 3 data sets, especially for the first data set, we can see that our method, DRIKE, achieves the best result in terms of ESR, best result in terms of PC with a substantial margin, whereas it achieves the second best result in terms of retention rate. So overall, it's a much better kind of trade-off compared to the previous method, which is the static retrieval and fixed number of examples in IKE. And in the other 2 data sets, we can see that it actually outperforms IKE in all of these metrics. You can see this is pretty impressive considering that we're only using a linear head as the trainable layer for the APM. So, so these are pretty much the 2 examples I wanted to introduce. But we have some ongoing efforts in some other problems. But in general, the takeaways for APMs is that lightweight APMs can indeed be used to steer LLM downstream tasks such as speculative sampling and in context knowledge editing. We expect it should work on all kinds of different scenarios. And the advantage is that it is very low cost in terms of both training and inference. It's fast, it's flexible, doesn't need to change or tweak the LLMs. It works for black box settings sometimes. I say sometimes because in a speculative sampling framework, we still need access to the target, to the LLMs. And so overall, in terms of methodology, it still follows the ILVR framework. And the key here is that we do need an automatically verifiable reward function. And in both of these works, we treat the frozen LLM as part of the environment. So if you're interested in checking out, we have released the code for both projects, and you can find them on my website. So at last, I wanted to kind of conclude with a belief or philosophy that I have. So I believe that the future of AGI is not just a single gigantic model, but it's a community of big foundational models and small or even tiny auxiliary models. And that should conclude it. And I'm happy to take questions.
Okay, thank you, Professor Chen, for the enlightening talk. So we're now open the floor for questions from the audience. So please drop them in the live chat. Okay, let's see. The first question here is for reinforcement learning, what do you see as its main limitations, and where do you think it needs to evolve next?
Well, I think on a bigger picture, a very critical step is to still like going back to the blog post on the welcome to the era of experience. For IELTS frameworks to work still needs a lot of experiences, right? Whenever we do have these experiences, then IELTS can work. For example, it started from the simulators. Whenever we have a good simulator, for example, in Atari games, we have a lot of experience and millions of game episodes. Then we can use those experience to train a good IELTS policy. And then later on, whenever we have lots of human feedback, right? Those are also kind of data to train the IELTS algorithms. And then even more recently, we have those verifiable reward from the reasoning chains, right? If we do have these experiences, then IELTS can work. But if we don't, it's very hard for IELTS to work. So a critical step here is in some of the domains problems, for example, in math or in reasoning, in some of the question answers where you do have answers, or some coding domains where you do have those easily accessible or automatically verifiable rewards, then you do have those experiences. But what about the other domains, right? What about an open question? Or like just daily conversations, like in humans, we a lot of times we talk to some people, we will realize immediately like if we're saying something correct or not, right? We can just check the correctness of what we said based on, for example, the look of a person. But how can LLMs generate those kind of experiences very easily in a large amount? That's I think it's a major limitation, and also it's a very important next step that we should figure out.
Okay, thank you. Next question is quite similar. Like, in your experience, what are the biggest practical bottlenecks? Like, what are the biggest challenges when applying reinforcement learning to LLMs at scale?
Well, so of course you need data. That's the first question. You need a lot of good quality data, not just like random data. A lot of data have noise. If you do have noises, it makes it even harder to train. Except for data, I think there are, and like to practical engineering, there are still a lot of bottlenecks, right? First of all, you have to figure out what is the underlying problem, right? Sometimes you don't have an explicit idea of how you should define this problem in the first place, right? What is the MDP? What should you design as a state? What is the action, and what is the reward? A lot of these practical engineering questions you should figure out in the first place. And there are also indeed, like before the LM era, there's a lot of like different choices for your algorithms. You can use policy-based methods. You can use value-based methods. Um, if you're talking about like the pre-LM era, there's a lot of these design choices you have to make, and these different design choices are based on your understanding or your domain knowledge. And a lot of times people say that IELTS doesn't work, and actually, in my understanding or in my point of view, IELTS doesn't work because you don't really have a niche IELTS engineer to really work out a lot of engineering questions, like what algorithm you're going to use. Is it PPO, GRPO, or even DQN? And how you're going to like design some of the nuances in your reward. Are you going to give a penalty, like a KR divergence penalty? Are you going to design some schedules of your learning rates? A lot of these small choices going to make a big difference in IELTS training. So that's, I think, some of the bottlenecks.
Okay, thank you. Okay, the last question we have here is, do you expect reinforcement learning to remain a core component of LLM training, or do you expect it to be gradually replaced by another paradigm?
Yeah, so I think that's I don't have a clear answer to that. I mean, as an IO researcher, like I said, it's like you're always riding a roller coaster. Sometimes you have apps, right? You feel that it's really working, but sometimes you feel it doesn't work. So the key here is still like, in the future, can people find out a way to efficiently, seamlessly generate training data? Like word model is maybe one promising direction, and maybe there are some other ways to generate these experiences. If people can find out a way to do that, then I think it's definitely gonna stay as a core component, and that's inevitable in any LLM training pipelines. But if you don't, then I think that people are probably just gonna stuck at DeepSeek R1 or IO HF kind of frameworks.
Okay, thank you. Yeah, I think that brings us to the end of today's session. So huge thanks again to Professor Chen for sharing his expertise and great vision. We'll share the replay and the slides on our community channels, so stay connected and don't miss the next episode of the AI co-learning program. Yeah, see you guys.
Thank you.
Thank you.